Now in this section, we'll talk about work in the physics sense, and how dot product and projection and decomposition ties in with work. So a reminder, in the simple physics setting, if you have a force F that's displacing an object over a distance d, then the work performed by that force is F times d, the amount of force times the distance. This is valid when the force acts along the line of travel, like if there's no other forces acting or some constrained motion in some way. And it has to be a constant force, and it has to be a straight line distance. But in assuming all that, this is the formula: work equals force times distance. Well, what if it's a more complicated setup? What if the force is a vector, and d is a vector, and they don't necessarily point in the same direction? What then? The answer is that the component of force that counts for work, the component of the force that counts for work is or in other words, the component of the force that acts directly on the object, that is the component of F parallel to the direction of displacement. So the picture here is, I've got some displacement d, an object that's moving along this vector. And then we've got a force that doesn't necessarily point in the same direction. We'll do some examples next. Well, in this case, the component that counts is the parallel component. That's the one that counts for work. The other component, the perpendicular component, doesn't count for work. The reason for that is kind of getting into some physics stuff, and it's mostly a story for another day, or a story for a physics class. That just is how it is. So I don't want to get too much into the details, but I'll just say briefly why F-perp doesn't count for work. Well, sort of the brief reason is, you've got this force that's pushing the object to the side, and yet it is not moving to the side. Right? There's this purple vector that's pushing our green object to the side, and yet the green object is not moving to the side. It's moving along this vector d instead. Why is that? Well, presumably there must be some other force, like gravity or friction or something, that's pushing the object in the opposite direction to the purple vector to counteract it and to keep the object on this path. And so whatever work F-perp does gets canceled out by that opposite force. And so you end up with net zero work. Well, if you might want to ask a physicist, and they'll give you a little bit better, more detailed and accurate answer than that. But I think that's the basic idea there for why F-perp doesn't count for work, and F parallel is the only part that does count for work. So in our previous formula, we were doing a scalar F times the distance, and the scalar that we need is the scalar projection, the component of F along D. So there's a dot product F dot D divided by the length of the displacement. And then we're going to multiply that by the distance, the length of the displacement. So we end up with the scalar force, which is F dot D over magnitude of D, times the distance, magnitude of D. And, according to algebra, those things cancel, and you just end up with F dot D as the result for our vector situation. And now the exclamation points are here because if you look back at the previous slide, when it was scalar, it was F times D, just a scalar F times a scalar D. And we went through this whole thing with vectors and projections, and in the end, it all simplifies down, and we got F dot product D. It's so similar to the previous formula, despite all the steps we had to go through to figure this out. I think that's kind of neat. All right, so that's how scalar projections and dot products tie in with work. Here's an example. How much work does it take to slide a box 20 meters up an incline of 30 degrees if it is pushed by a force of 200 newtons that's acting at an angle of 45 degrees above horizontal? So the picture here is, here's the triangle is the incline of 30 degrees. And we have a large object, a box, and a force that's pushing it with a force of 200 newtons. However, the force is not just pushing it along the ramp. The force is actually pushing a little bit up above the angle of the ramp. And then presumably gravity is part of the picture that's pushing it down. So when you add the gravity vector on, force vector on there, you get a net force. So this is gravity. A net force at a 30-degree angle. So that's what I'm... Yeah, okay, so we get a net force at a 30-degree angle. So how much work is being done here? And I don't have an answer slide. The answer is the amount of work is the force vector dot product the displacement vector. The force vector has a magnitude of 200 degrees and an angle of 45 degrees. So 200, and the cosine and sine are root 2 over 2. And we're going to dot product that with the displacement vector. A lot of green. Let me switch to another color. Our displacement vector is 20 meters, and it's at an angle of 30 degrees. So cosine 30, sine 30. So we have 20 times root 3 over 2, and then 20 times 1/2. So if we simplify, we'd have 100 root 2, 100 root 2, dotted with 10 root 3, 10. And that dot product is 1,000 root 6 plus 1,000 root 2. And now I left out units while I was working this out. The force is 200 newtons and the distance is 20 meters. So the green vector is in newtons and the purple vector is in meters. And overall we have Newton meters. Do you remember the other name for Newton meters? These are joules. A joule is a Newton meter. A question for you. The picture shown is in R2. There's no funny 3D stuff here. If the force vector F is minus 4j, it's not drawn in the picture, but it's minus 4j, then the total work from O to which point will be the most positive? A, B, C, or D? So the answer is D. Our force vector is this one, minus 4j. That's pointing straight down. So which one has the most positive dot product with our green vector? Or in other words, which one has the biggest component in that direction? And the answer is D. Goes the furthest down. All right, that's it for reviewing dot product, projection and decomposition, and then applying the projection and decomposition to work. We'll see plenty more applications of dot products and projections and decompositions later on. Okay, bye.